So let's get started for today's class. My name is Mihir Thakkar and I'm the founder and instructor at CodeHeroku. We are going to do a quick recap like we usually do. And the agenda for today is the unsupervised learning algorithms. We are going to see a popular unsupervised machine learning algorithm, which is called as clustering. And within clustering, we are going to study a specific type of method, which is called as k-means. And eventually, we want to implement this clustering algorithm in Python. We just don't want to study theory about it, but we also want to make sure that when you guys go from this class with a sense of being able to make something by yourself. Okay, we have seen supervised machine learning until now. In the first module of this course, you have seen a lot of supervised machine learning algorithms. And the last one that we did, we were doing classification problems using machine learning, right? In those scenarios, what we are given is a data set like this. Over here, you have been given a data set where you are given house size, location, the age of the house, and your job as a machine learning engineer is, by looking at this examples over here, you need to predict what will be the scenario be for these next two cases. Over here, you just have three examples, but it's just a dummy data set. In real life, you would have thousands or millions of records that you look at. And then based on what you see in your training data, you would come up to predict the targets or the labels for the test data points as well. So these points are your training data sets and these are your test data points. Okay, by now you guys should be familiar with these terms. But what happens when you come across a scenario like this one? Over here, what you see is researchers are trying to analyze the MRI scans of your brain. And based on the different activity a person does, different parts of brain might get activated. Okay. And to come up with these visualizations, they were not given any labeled data sets, right? They weren't told that, look at 10 million records of brain scans and this is what we have found, and now predict what you're going to get. So there is no previous research done, a similar research done, and there is no previous labeled data set there, right? It's not possible. When we are trying to make sense of our data, we come across situations where there is no prior work done in this field, and there are no data sets which are available. There aren't any labeled data sets which are available. Over here, they had lots of MRI scans which might be available in a hospital's database, but no meaningful information would have been generated, because think of the output that an MRI machine might give. It could be the electrical pulses or MRI images, which would contain the data rows or the features in millions or even more than that. Often we come across situations like these where there isn't a formal problem, or we know that we kind of know what we are looking for, but we still don't have any prior information about the subject itself. At that point, the second type of machine learning algorithm, which is unsupervised machine learning algorithm, comes to our rescue. What you do for an unsupervised machine learning algorithm is, let's say you're given a bunch of fruits in this case, or in a real life setting, it could be images of a fruit which are given to a system, right? So you're given a bunch of fruits, or images of these fruits are fed to a machine learning algorithm. This goes to an unsupervised machine learning algorithm, and what it does is, based on the things that it sees, maybe the size, color, and whatever features that the machine learning engineer chooses, it would classify them into three buckets. Over here, our unsupervised machine learning algorithm looked at this information or the data set which was given to us, and it said, okay, I think that all the images which are red in color, which look like this, are in bucket one. All the ones which are oranges or have a shape like this are in bucket two, and so on. But note, at this point, it doesn't know that these are apples or these are oranges. We haven't told our unsupervised machine learning algorithm anything as such over here. And based on what the similarities or a structure that it sees, it tries to find that hidden structure in this data set which is available over here, and it tries to make sense out of it. Okay, so my question to you guys is, how is it different than classification? Over here, you could say that I made three classes, right? I could just change the word cluster to classes, right? So how is this different than a classification problem? In a classification problem, we still have those labels, right? We are told over here that, you know what, we take 100 images of apples, and this is an apple, this is an orange, this is a mango, right? And in this case over here, we are not given any such information. We are just trying to find hidden patterns in this data over here. And that's the first thing that we know said about the differences between a supervised machine learning algorithm and an unsupervised machine learning algorithm. That within a supervised machine learning algorithm, you'll find that you have a labeled data set to work with. And for an unsupervised machine learning algorithm, the labels or the targets in this case, which was in our previous example, which was the what fruit is it, that's totally unknown. We know that those are similar images, but we don't know what they are. For a supervised machine learning algorithm, you are gonna come up with these two tasks. The one is the prediction. Given a set of past points, you need to predict what's going to happen in the future, or you're trying to classify things based on the parameters of a given item. Let's say if a user likes or dislikes a movie, and you are given 20 or 100 movies in past that he has liked or disliked, and then you are given another movie now, and you have been told that, based on what tell me, will a user like or dislike a movie? So either we're trying to predict something or we are trying to classify things, okay? Whereas an unsupervised machine learning algorithm is trying to find hidden patterns in the unlabeled data. It is trying to find a structure in them and find similarities in the content there. Overall, what you could say is supervised machine learning algorithm is a problem which is more formalized, mathematically speaking, or even conceptually. For an unsupervised machine learning algorithm, you kind of don't know what you're looking for. So the problem itself is ambiguous in that case. So let's see where do you find unsupervised machine learning algorithm in real life. One of the very commonly used applications of unsupervised machine learning algorithms is to reduce the dimensionality of a data set. The picture that you see on the right is called something called as an eigenfaces, which comes from eigenvalues of a data set. So what you're trying to do is, this is a classic example where you would use an unsupervised machine learning algorithm to reduce the dimension of a data set. Over here, someone is trying to make a face recognizer, right? So that's why we have so many faces. Given that you need to make a face recognition system, can someone tell me what will be the input to that machine learning algorithm be? So Sanoy Mitra says eyes, but Sanoy, let's say you take a picture of a person and you need to find which person is it. So at this point, you don't really know where that eye is in that picture, first of all. And if you knew that, it could give you an intuition on who that person is, right? So the main task, again, then you're trying to deal with a smaller problem, will be like an eye recognition, and then you go one step up. So you have that intuition correct over there, is that you could split your face into smaller parts and then try to identify person based on that. The intuition is correct over there, but how do you go about detecting the eye itself? Suchit thinks that those are pixels. Jai thinks those are expressions. To a machine learning system, you can't give expression as a raw input, right? So imagine that a person is standing in front of a camera, and this camera is connected to your machine learning black box, right? So what's the first stage of the input there? Those are pixels, right? The pixels from the image are the features that we are giving. And let's say even if you take a picture of 512 cross 512 pixels, which is not that good of a resolution, but even with that, imagine how many features would you end up with, which is like no more than 1,000 or no even more, right? Which is like 25,000 or more features. So given that, what a dimensionality reduction algorithm does is tries to find features or pixels in that case which have most impact on the output of that system. Over here, a famous algorithm which is called PCA is used to create these eigenfaces, which is kind of averages. If you closely notice, the first image over here is actually the average of all the faces on that data set, which looks weird over here, but that's what it is. And this is the first principal component, the second, the third, and so on. Okay. So we are going to study PCA in our coming classes. Don't worry too much about it, but that's the basic idea. You're trying to reduce the number of points or the parameters that you're trying to work with to a smaller number. Okay. And then look at an example like this one. Over here, someone is trying to make an image compression algorithm. The original image might have more colors. And if you're trying to compress that image, you have to lose some of the color information. So how do you get the regions of the image which are close to each other? Over here, you're seeing that the color of that image, there will be some loss. It's not a lossless compression, but there is some loss in this case. But your unsupervised machine learning algorithm might help you to come up with the colors which are close to each other, and eventually you might be able to reduce it. So I have a question from Suchit saying, can we use PCA in digit recognizer that we saw in the previous session? Yes, definitely. So try it out. What happens if you try to use PCA in the digit recognizer that we built? The problem or the challenge that you might arise is the recognition phase. We were using SVM, right? Support vector machines, which is something which is good at dealing with higher dimensions. And with PCA, you're trying to reduce the dimensions, right? So that match of reducing dimensions with the classifier that you use is going to play a critical role in the performance or the results that you get. Okay, so you don't want to select a classifier which is good with high number of features, whereas with PCA you're trying to reduce the number of features, right? All right, so the next one is anomaly detection, right? In many cases, let's say if you have a enterprise, you are a company and you're trying to make sense of the data which is the network information which is going through your company. So you want to make sure that if there is an anomaly, if someone is trying to hack into your systems or something like that, you want to make sure that you flag it. So how do you go about doing that? There is no data set that you have as such, right? So you might create a supervised machine learning data set from it, but I'm not sure how good it will perform with that. But what you could do is, you could make a system which continuously adapts itself as well, and with unsupervised machine learning to detect any anomalies in the data set. Another important example for or a use case for unsupervised machine learning is called topic modeling, or trying to categorize things into different buckets without any prior information, right? So the image that you see over here is from NIH, and they were trying to model all the grants that they have given in past 10-20 years. So they looked at their databases and said, these are the grants that we have given in last 20 years. So can we make a sense of where are we spending our money? So they would just give this raw data to a clustering algorithm, and this is what the clustering algorithm came up with, right? So they could clearly now see what is related to what. You could also find connections between these topics, as well as if they are color coded in a way, you could also predict how much did they spend. Okay, so clustering will also give you a sense of how is your data connected, which is another important I would say use case for machine learning or non-supervised machine learning, is trying to find the connections between the data point itself, and how changing one parameter affects the other parameters, or how changing one data point will affect the other data point, to be more precise. In which of these scenarios would you most likely use an unsupervised machine learning algorithm? The first one is, given a set of images, you are interested in grouping the ones which are similar. Or the second one, with given a training data about users' preferences, you are interested in knowing whether they would like or dislike a movie. Or the third one, which is given a set of 1,000 features, you are interested in finding features that capture maximum variance in the data. Okay, so the correct answer to this one is 1 and 3, both. First of all, tell why second is not correct. So we are given a training data about a user preferences. Okay, so and looking at the training data, you would classify whether a user would like or dislike a movie, and that's why we are saying that no, this is definitely not the case. Okay, so for those who have said only one, let me tell you that three is also included, right? So given a set of 1,000 features, you are interested in finding features that capture maximum variance. You are trying to explore your data itself, right? And as you saw over here, dimensionality reduction is an important application for unsupervised machine learning. Over here, the raw image would have been of 512 by 512 color pixels, right? Even if you, after you convert into grayscale, I would say the first principal component over here is much more compressed. It has a very few ranges of pixel over here compared to a grayscale image that you would normally see, right? So the PCA of a image will give you, the first 7 or 8 components which are giving most variance to that data. This is also an important application or a use case for unsupervised machine learning. Okay, we know that unsupervised machine learning is cool, I guess, and we need to now learn how do you go about implementing it. Let's see how you would go about doing that. We have already seen one application over where we were using the same example as a classification example, but now I've tweaked it a little and said this is clustering. Over here, assume that you are not given any prior information on which movie a user likes or dislikes, and your unsupervised machine learning algorithm has now come up with two patterns in the data. It saw these two features. On the x-axis we have the movie time, and on the y-axis it was IMDb rating. Your unsupervised machine learning algorithm saw this data set and said that, you know what, I think this set over here is similar and this set over here is similar. Okay, so it still doesn't know whether these are the movie that the user likes and these are the movie that it doesn't like. It doesn't know that. Okay, it's not its job to know that. The only thing it did is it created these two clusters for us. So now my task is, how do you go about doing something like this? Let's say you are given this data set like this, everything is black. Now your job is to color some of these as red, some of these as green. Okay, and to do that intuitively in your mind, you can obviously look at these two things and say, okay, these are red and these are green. So but what did you use intuitively in your mind right now to color those two segments out, or cluster those two things? So what do we need for clustering? So distance from other points is important, right? So the first thing that we need is some way to measure the proximity of these points. So the first thing that we need is, to do these implement clustering algorithm, we need to have some sort of proximity measure. And have we studied any proximity measures already in this class? Yep, Euclidean distance. What was the other one that we have done? So Euclidean distance will measure the magnitude of the vectors. It will measure how far apart in the Euclidean space you are. Another way to look at it is also by looking at something called as a Manhattan distance. Have you guys heard of it? It's also called city block distance, or no, you can look it up. Just another way of coming up with how far you are. And you could also use something like cosine distance. Most likely it won't be used, you won't come across for clustering applications, even though there might be some cases where the things which are apart in angular distances, you want to get a sense of those things. So cosine distances are the other one. If you haven't seen our previous class on where we talk about Euclidean distances and cosine distances, please have a look at those videos as well. Okay, how do you go about calculating the Euclidean distance? I want to calculate the Euclidean distance between this point and this point. So what would you do? It's this d over here, right? It's simply root of x1 minus x2 the whole square plus y1 minus y2 the whole square, right? You just subtract the x coordinates, y coordinates, just use Pythagoras theorem over here, and you could imagine a triangle over here. You can get Euclidean distance with that. That you also need is, let's say you calculate Euclidean distances and you say that, what, these points are, I think that these are close, these are close. The second thing that you also need is, now once you create your cluster, what you also need to know what a good cluster looks like, right? And there are some measures that see how close apart these points are, or how far these two clusters are. And based on the evaluation criteria that you use, your problem or at hand, or your algorithm that you'll choose, you will tweak that a little as well. So that's like a bigger picture, right? That's how you would approach this problem. But today we are going to study about one such specific approach to clustering, which is called as k-means, and it's by far one of the most popular algorithms for clustering. So we are going to go about in depth in how k-means goes about finding those clusters. At a high level, we know that we need two things. The first one is a distance measure, which we could use as a Euclidean distance, a Manhattan distance, or maybe even cosine distances, right? And the second one is you need some sort of evaluation criteria, right? So you need some sort of evaluation criteria to look at those clusters and see whether you have got a good cluster or not. So keep these two things in mind as we go ahead. So this is how the k-means works. Let's imagine that we have the same data set as you saw before, okay? And you are given this set of points. Now these points are not labeled. These visually they look separate, and you know that now eventually you should come up with an answer which has all these points grouped together and all these points grouped together. Can someone tell me if you have heard of any other iterative methods from our previous classes, or if you might have studied machine learning or any other algorithm that you have seen somewhere else? What are some examples of an iterative algorithm? Yep, gradient descent, bisection, these are iterative algorithms, right? If you have studied searching and sorting as well, so you try to sort things, those are iterative algorithms, right? They perform iterations on your data set, and you eventually come up with a good answer. So k-means, the reason why it is called k-means, that it comes with k centroids of the cluster. Over here, by looking at the data, we knew that there were only two clusters. So let's say we assume that we start with k is equal to 2. So we have two crosses over here. These crosses are also called as centroids of that cluster, okay? So right now we are saying that our cluster is at this point, around this, okay? At this point in the algorithm, we are just saying that our cluster is just at this point, this x over here. So we are saying that this is where these two clusters are. And how did we come to this point? Randomly. We just select 2 points at random, and how you choose those points are also critical. We'll come to that in a minute, but that will also affect performance of your algorithm. So let's say you come over here and you initialize these two crosses or these two centroids randomly at your point, okay? So what k-means is going to do next is it is trying to find the distance from all these points to these clusters, okay? So it will calculate the distance between this white point with this red x, all the blue points with each of these points, okay? So you will calculate distance from all these points. And what it says is, given the points which are closest to these red cross over here, the red centroid over here, color all of them with red. And when I say color all of them with red, it means like assign this cluster 1 or the cluster red to all these points. So all these points right now are in our red cluster, and all these points are in our blue cluster. So it saw that every point asks itself, where am I closest to? Am I close to red or am I close to blue? And this point said, I'm close to red, I'm close to red, I'm close to red. So it marked itself as red, okay? And similarly for all these points, they said, where am I closest to? Am I close to blue or red? And they'll mark themselves as red or blue, okay? And again, this is called the assignment step, because each point is being assigned to a particular cluster over here right now, okay? In the next step, what k-means does is, okay, once this assignment is complete, let's see what do we have in red. So it collects all the points which are in red now. Then it asks itself, okay, once I know these are all red points, what is the mean of all these points? So it says, okay, the mean is somewhere over here. The next step, what it is going to do is, now that it knows that the mean is over here, it is going to move this x to that position. Okay, so it is trying to get close to where the k is trying to get close to the mean over here, right? K means, I guess that's how they came up with the k and the mean, right? So the k is, the centroid is trying to come up to this mean location over here. So now he's asking, what happens if you come up with a point over here which is equidistant from red and x? Well, in that case, when you are implementing an algorithm, you will have to either just select one or the other. Okay, so let's say you're trying to implement it, your exact lines of statement or the pseudocode would look something like this. It is going to say, if I'm closest to red, or no, if the distance from red is greater than or equal to something, or no, if distance is greater than something, do this. If distance is less than something, do this. Else, just assign myself to blue. Okay, so you just have a third condition over there saying that, no, which catches all. So in the equality case, so you just randomly assign yourself to one cluster if you are equidistant, right? So our x moved to this point. Okay, now blue is going to do the same. It is going to calculate the mean of all the blue points, and then it is going to move its centroid to that location over there. So blue moved itself to a location which was the mean of all its points. Okay, so now at this point, this is the scenario that we have. Now there are some red crosses over here, there are some blues over here. So now let's see what happens. All points right now are going to ask the question to themselves again, am I close to red or am I close to blue? Am I close to red or am I close to blue? Right, so each point is going to ask itself the same question again, and based on where it is closest to, they will color themselves as red or blue. In this case, what happened was these points ended up being close to this blue, and this red cross being, is closest to all these red points. So these points assign themselves to, the red cluster. And you do the same step again. Okay, so what you're going to see is, eventually you will come up with something like this. Your red cross moved to this point because that's where most red points are. Your blue cross moved inside over there, and because that's where all your blue points are. But there is just one point which is mislabeled over here, and there are these 3 points over here. Next time when they ask this question to themselves, where am I closest to, they'll end up falling in the right cluster again. So you end up with something like this, wherein after a point, what is going to happen is your x over here is not going to move enough. Okay, because there is no space to move, or every time anything happens, each point says that I'm in the same cluster, so nothing happens, and your x or the centroid stop moving after a point. So you eventually will converge. But my question to you is, and I already given a hint to you guys, we have seen in gradient descent that always you don't end up with a correct answer over there. What's the correct answer? You don't end up with the best possible solution to the given problem, right? So there are some local minimas. What do you think is the case with k-means? Will it always end up classifying these clusters perfectly? Let me go back over here. What if the choice gets selected in the wrong cluster? So no, you are saying that no, it won't end up with the right answer always. And this choice over here, what we are saying is, no, that is certain that whoever is closest to that point will assign itself. But yeah, all of you have the intuition correct over there that no, it's not going to always end up with the right answer over there, and we'll see why. So I have a question for you. The distortion of a cluster is given by this formula below. Calculate the distortion of clustering algorithm with the following values. Okay, so you are given this cluster over here. Okay, and at this point, this has converged. Okay, now your x is not moving anymore. But the distortion, or how well we have did in this clustering algorithm, is given by the distance between this centroid and the mean of these points. Okay, or the distance between this centroid and, sorry, not the mean, because this centroid is at the mean it will be at the mean always. But what is the distance between the centroid and each of these points? How closely we have been able to estimate a cluster properly will be given by this formula over here, which is for the distortion of that particular cluster. So go ahead and calculate the distortion for that. Guys, it is pretty straightforward. You just have to do square the differences between each of the x and the x over here, right? And just square them up and then add all of that together. Let me answer Grusha's question. We took 2 centroids initially over here, but we didn't know that the data will have 2 clusters, right? So the choice of k is totally up to you, okay? And we are gonna see in next 1 or 2 slides, how do you go about deciding how many centroids to take. Over here we are, just to explain you, I just said, what, let's say we take 2 centroids or 2 clusters, but by even looking at the data, you knew that there were only 2 clusters. But how about when you are in higher dimensions, like when you have like 1000 features, you can't even visualize that, right? But the approach is going to be the same. You start with, let's say a number of clusters between, let's say 3 and 10, and then you see for what kind of clusters you are getting good results, okay? And what do you mean by result is the distortion, right? The distortion measure is going to give you how well you did with your clustering. So we are going to look at our distortion for different number of clusters, and based on where we get good results, we are going to select the number of k or number of centroids or the number of clusters. Yeah, over here, if you would have started with 3 over here, right? So you would end up with 3 clusters, which will not be optimum, right? So you will end up with the value of distortion, which will be much higher, or in some cases, it won't be that good. Yep, if the distortion is less, that means better the result. So it's just one of the parameters, or one way to look at how well we did. Okay, it's not just the only way that you could look at, but looking at the distortion, you can say how well your clustering algorithm performed. Okay, answer over there, which is 7, right? So that's how you would go about calculating it. You just take a difference between all these points over there. So on the second point, there is no error, right? So 3,3 and 3,3, there is no distance between that. So that's 0. Now on the third one, you have 2 minus 3 the whole square, and again 2 minus 3 the whole square. So the total will come up to 7. Okay. So coming to Grusha's question, how do we go about selecting the number of clusters, right? And the answer to that is you don't know at start, what the right number of k's. So you start off with something, let's say you start off with one number of cluster as 1 over here, and you see that the distortion is 3.5. So you say, okay, let me do k means once more. You say number of clusters as 2, and you say distortion is something, it's around 1.5 or 1.7. And after a point, you reach to a point where now you get this elbow-like structure. So imagine like this is your shoulder, and this is your elbow, and maybe this is your arm somewhere, right? And this is your hand over here, right? So what you do is you select a point which is at this elbow location, which is around 3. And the reason for that is after this, you are just getting some incrementally better results, right? So you're not getting significant improvement in your distortion. So it doesn't make sense to do these many iterations from a computation standpoint, right? Because remember, even though k-means as a whole, it's efficient, but if you have so many data points, the number of iterations do matter. So after a point, you say that, what, I'm just going to get incrementally better results. So it doesn't make more sense. Over here, what we are seeing is what we call as the elbow method to determine how many number of clusters we should choose, right? So on the x-axis, we have the k, which is the number of clusters that we are selecting. Okay. And on the y-axis, we have the distortion. How did we come up with the distortion? We just calculated, right? So you guys know how to calculate distortion. You start off saying that, okay, let me start with k as 1. And how much distortion do I have? I have 3.5. And let's say for 2, how much do I have? Around 1.7. Around 3, I have around 1, right? You look at this graph and say that, what, this part after 3, I'm just getting incrementally better results. So there is no point in me choosing more than 4 or 5 clusters. So I'm going to choose this point in this structure, which looks like an elbow, and I'm going to choose this point, which is 3. And that's how you would go about determining how many clusters you should use for your k-means clustering. Questions is, so convergence depends on k. Okay, so that's my question to you. I already asked this question to you guys, and you said that no, you don't always converge to the right answer or the best possible solution, right? Let's say you end up with a situation like this, and in the previous one I did cheat and say that, you know what, this blue point is closest to this red point, but even by looking at it, it is actually not that close, right? So it is more close to blue point over here. So let's say now your x's stop moving at this point. So what's going to happen? You're eventually going to end up saying that this is the right cluster, right? So you're going to cluster it like this. By looking at it, you're going to end up with a lot more distortion, even though you should have ended up with optimal number of k as 2, but still your distortion is going to be very large, right? Because distances from each of these points to this x is going to be very high, right? So again, I have told this answer to you, but my question to you is, what factor will determine will we converge to these two clusters or not? What is one critical step that we take which will determine, will we just forget about anything in general, just for this particular example? We know that the optimal number of clusters is 2 by just looking at the data, right? We selected k is equal to 2, but we still ended up with a situation like this where the x's are not moving anymore. So what led to this situation? How did we end up over here? And what will determine if you are going to end up in this situation? Again, I'm going to go back over here and I'm going to go through all the steps, and you need to tell me which step is the most critical. Okay. So yeah, that's one complete loop. So out of these three things, 1, 2, and 3, what is determining factor which will affect our convergence? You have 3 choices. Okay, this is the first choice, second choice, and this was the third choice. So Sanway says occurrence of a point near to a centroid, second choice. That is, the second one is not the correct answer, and Grusha got that one right. The first one, which is the most critical one, where do we start, right? So we are starting randomly at this, in this space over here. Based on where we start, we're going to end up with different solution, and depending on where we initialize these centroids, we are going to end up with different solutions. So it is very, I would say, biased towards your initial locations. Okay. So one approach to know what you do is, a lot of people use an approach where they would initialize these centroids right on the top of one of these points in this data point. Okay, so either you would start this red over here on this point and a blue on some other point. So you'll just place them randomly onto the point itself. But again, there is no guarantee that you will end up with an optimal solution. So what's another problem with k-means? We have already seen this before. If someone would have given you this data and imagine that everything is same colored, so what were the 2 clusters that you would have given out just by looking at the data? Yeah, Krishna got that right. Inner circle and the outer circle, right? But this is what k-means is giving it. K-means is saying that segment it like this, which is definitely not the optimal solution for this case. The reason is, k-means doesn't work with the data set which is not linearly separable. So in this one, it is not linearly separable, and thus we are ending up with a solution that k-means is giving us. In our last classifier that we studied, which was SVM classifier, we had that kernel method that we were applying to make it work with in the nonlinear case. So if you want to try out something like that, can you apply a nonlinear kernel to that data and then apply k-means? Does it work after that? Tell me if that works. Okay. And it is also sensitive to outliers. So in this case over here, forget about these lines which are drawn, right? And you were to come up with 2 clusters. So Grusha, your answer to your question is just by looking at the data and knowing the domain itself, right? And that's what makes machine learning difficult. Otherwise, everyone would have just taken the data and applied it to the methods which are available in scikit-learn and got great results, right? But the reason why machine learning in practice. So, okay, so understanding it, learning it is not difficult. Okay, don't get me wrong. I always tell our friends, or no, I always tell all our students that learning machine learning is not difficult. Applying machine learning is. So just by the only way to come up with saying that whether the data is linearly separable or not is either having some domain knowledge about it, and either visualizing it. And how much would you visualize, right? Either you could visualize in 2 dimensions, right? What is your data has more than a million features, uh, quite possible, right? So what you do in those cases, you don't know that always. So coming to this point over here, the optimal clusters over here would have been the cluster 1 over here and cluster 2 over here, right? Or maybe if you want, you can take this point over here as well and cluster 2 over here. But what k-means ended up doing was, it created 2 clusters like this, because maybe the centroid started here somewhere and it got stuck after that point. It couldn't move anymore. So it created these 2 clusters like this one, which was not an optimal solution. So k-means is also prone to the outliers over there. One way to get rid of it is to first visualize, or first inspect your data, go over it, and if there are any points which which have very high variance, you just get rid of them before applying your k-means. Okay, so let's go ahead and start building it. I think we have gone into enough depth about understanding what are some challenges with k-means and what are its applications. We haven't done like applications k-means specifically, but we do understand where clustering and unsupervised machine learning is used, I guess, right? So let's go ahead and implement this, build it in Python. I'm gonna give this link to you guys. So go over here and click on the download button over here, download it, put it in your zip file, put the zip file on your desktop somewhere and unzip it. You can just get rid of this Mac OS X folder if you want. So let's go ahead and now look at this data set first. We're just gonna open the data set up. We have 2 features. Let me tell that to you. We have just 2 features over here, which is V1 and V2. Okay, that's it. And all these points over here are just with these 2 features, we are gonna use k-means to get this data. It is a simulated data, so it's not a real world data, but it's a simulated data. We are gonna use k-means on the simulated data and try to come up with clusters. Okay, so let me close this up. And this k-means completed is for your reference at the end if you need to look at it. Let's open the k-means.py file. I'm going to open it in Sublime. You can open it with some other text editor if you are used to for working with in Python, and have a look at what I already have for you. This time we have a little more number of helper functions than I generally give, but this was for so that you don't spend a lot of time doing matplotlib and those kind of things. Just skim over it, go through it, and see if there is something which is you don't get anything. Like, don't worry about these individual methods. If you go and look up the documentation, you would understand what that is. It's not rocket science, but go through the structure of the program in terms of the steps that I have written over here and see if there is something that you don't understand. So let's get started. And the first thing that we're going to do is read our data set in over here. Okay, we have done this a lot of times in our previous class. If you are coming to our class for the first time, here's what our basic philosophy is. We don't try to give each and every line to our students when we are writing Python code. We want you to go to Google and find out which line of code you're going to use to read your data set. And we want to use pandas library over here that we are using. So we are saying import pandas as PD. Can someone tell me which line are you going to use? Everyone else go ahead and use the line pd.read_csv and get your data frame in your program. Okay, so let me go ahead and do that as well. So we're going to say data frame is equal to, you're going to say pd.read_csv, and let's say dataset.csv. Right, Let's save that. Let's print our data frame and make sure we are getting that right. We're going to say print data frame dot head over here to make sure that we are getting the data frame. Save it, build it using Control plus B. So you're going to say Control B and you're going to build that, and something is off and it's saying that there is an indentation error on line 56 over here. Now it says it's over here. Oh, I know why is that happening. We don't have any lines in the while loop over here. That's the reason. So we need to have something in the while loop. So please make sure you go over here and you comment out this while loop. Let me run this. Yep, we got it. We got data frame.head. So we have v1 and v2, and there are obviously more lines in this data set, but we see that these are the first 4 or 5. Let me just show you how many. So we have about 3000 rows and we have 2 features. So we have 3000 data points and 2 features over here. Right, so let's get our features now. Let's get F1 from our data frame. We're going to say F1 is data frame of the column names over here actually is V1. So let's just say V1 over here. Okay, and F2 is data frame of V2. So I want to plot these things out on our matplotlib. Okay, so we have done it in different ways for different programs, I guess, but this time what we are going to do is, because the way these helper functions are written, what we need to do is, you need to trust me on this, that we also need to create this feature vector X, which will be a list, and we are going to zip both of these things together. Okay, so we are just going to zip both our features together, and that's how we are going to pass it to the rest of our program. Okay, so this feature vector X will have all our features, which is going to be a list of tuples. Okay, now let's plot the data in centroids. So to do that, first we need to start off with K. Okay, so we don't know how the data looks like, or how is it organized. So let's just start with K is equal to 4. Okay, and we need to get random centroids, right? So we need to get the locations of these points on the graph, and we see over here that we have a function which is given to us which says get random centroid. It takes in a data set X, which is our feature vector, and the number of Ks that you have, right? So let's give it to it and let's get our centroids, and also see what it returns. It returns a C. Okay, so it seems like C is combination of Cx and Cy. Okay, so it's nothing different. It's combination. It's Cx and Cy packed in together over here. That's what C gives. So we are going to use the same thing. Let's just copy this thing from here. These are the 3 things that our get random centroid method returns. So I'm just going to give the same thing over here, C, Cx, and Cy, and let's say get random centroids. We are going to pass our data set X and the K. Okay, so this is going to give us the location of the centroids on the graph there. All right. So the next thing that we're going to do is let's plot this thing so that we know how this data looks like. Okay, so let's say plot.scatter. That's how you would use matplotlib to plot your data points. So I'm going to say plot.scatter, and I'm going to say over here, let's just say F1 comma F2, because we want to plot all our points, right? So it's data frame of V1 and data frame of V2 over there. And we're going to say, let's say color equals to black over here. And let's say plot.scatter. Let's plot our centroids. So I'm going to say Cx, Cy, and I'm gonna use a different marker for this so that we know that these are separate from our regular data points. I'm using a star marker over here, okay? Or let's use D over here, which is the diamond. Yeah, this should be good, right? So we have all our plots, and all the only thing that we need to do now is do plot.show. Okay, save it, run it, and let's see what happens. Oh, we made a typo over here. I guess it came and just went away, right? There is something that we need to do to hold it. What's going wrong? We have plot.show over here. I guess let's try this. And does that change anything? For some reason, our plot is not staying up there. Can someone tell me why would that happen? Can you guys try it out over until here and let's troubleshoot it together? Okay. Let's see if that works. We're saying that I should do this. That's weird. Never saw that one. So right now it is okay, but it looks very odd to me because there are a lot of data points over here and we are just crowding everything up, right? So let's just do this. Let's make it a little pretty. Okay, so I'm just gonna reduce the size of this guy. Okay, I'm just gonna say let s equals to 7, and let's make our stars a little bigger. So I'm just gonna say s equals to, let's say, 100 maybe. Let's see, and use a different color for these guys as well. Okay, a little bit more better. I don't love it, but I can see that there are 3 clusters over here. These are our random Ks that we have selected. So I guess a better choice would have been to use KS3 over here, right? But we will experiment. We'll see how things go with different values of K. Right, so let's get inside this loop now. And let's come over here and let's say step 4, run k-means. Okay, so the part 1, let's uncomment the loop that we had commented up first. So let's get rid of these asterisks over here. All right, so while change in C is not 0, okay, so this was the line that was given to us. We need to make sure we need to run this loop until change in C is not 0, right? It's like, no, we have converge. So while the C is still changing, or while our centroids are still changing, you keep on doing k-means, right? So first we need to define what change in C is, right? And based on the 3 methods that are given above, so tell me which method will you use to find if C is changing or not, which is the coordinates of your centroids are changing or not. So we know that this loop, while loop, is not going to run. This is going to say that change in C is not defined, right? So what should I write over here? Change in C is equal to what? Either you just start with a very large number, right? So we know that a change in C is not 0, so it will definitely get inside the loop. Or you just calculate a distance. So where is our C first? Okay, so we have the C over here. Okay, just so that you know, we have the C, and now we need to see if the coordinates of the C has changed or not. So what should I write over here? And my hint to you guys is, now we are going to use one of these 3 helper function. Get random centroids is definitely not, and we are not trying to show the plot. So we are going to use the distance over here. So we need to calculate the distance to see if the centroid value is changing or not. Okay, so the way we are going to do it is we are going to say change in C is equal to, we are going to use distance and distance of C with, we need to have stored value of the old values of the C as well, right? Where was this centroid initially? We don't have it right now, but let's say if we had it, we would say C old over here, and you don't need anything over here. You don't need the axis over here. if we had C old, does everyone agree to me that the change in C should be the distance between your current C, your previous C, and we are just saying this axis over here. It doesn't matter over here. We're just going to say axis as none. By default, axis is set to the first, but we need axis as on the 0th element, and that's why we are just using axis as none. Okay, so we need to do something with the C old now. Right, so let's come with C old. Right, so we need to define what the C old is. Okay, so let's say we start with 0. Right, so let's say we start with all zeros. So we're gonna say np, which is numpy, and we're gonna say numpy dot zeros. Let's start with all zeros. So if C was 3 by 3 matrix, what should be the dimension of C old be? So Suchit says 3 comma 3. Does everyone agree to me and Suchit on that? If C is 3 comma 3, it's a 3 by 3 matrix. C old will be 3 by 3 matrix as well, right? So we are just gonna use C dot shape over here. Okay, so what this is telling is create a C old array of all zeros. Let's say we start with all zeros, and how much should be the dimension of that matrix? We're just gonna say, which is same as C dot shape. Whatever the size of the C is, use the same value over here as well. Okay, so let's get in over here. Okay, so we are going to say the cluster assignment, assign points to the closest cluster, right? So this is the part where each point is asking whether I am in cluster 1, cluster 2, or I'm in cluster 3, depending on how many clusters you have, right? So let's go over each of these points. So we're going to say for I in range, we're going to say length of x. For I in range, length of x, and lots x, this is our feature vector that we created, right? So for I in range of x, we are going to say distances of this x from the centroid. So distances of each of these x to the centroid. And I'm going to say we have a distance calculator there, right? So we're going to say distance. And I want to find the distance of this element with the centroid. So I'm going to say x element, and the centroid is C over here, right? So what we are saying is go over all your data points and get the distances of all x's to that centroids, to all centroids. And the way you're going to do it is we have a distance calculator. You're going to pass this data point x of I, and we're going to calculate the distance with all centroids. Okay, so if there were 4 centroids, you would get something like 0, 10, 20, 30. So something like this. So you're saying that this point is 0 distance away from the first cluster, 10 distance away, 20 distance or no, 20 units away, and 30 points away from the 4th centroid. Let's print it out as well. Let's print this guy. Print distances of x centroid, save it, and make sure that everything is running. We don't want this guy now. So let's just comment this thing. Okay, I'm just gonna go here, and we don't need the data frame. We don't need the plot.show here. Okay. So I'm just gonna comment our previous plots. Maybe this was a bad idea to print everything out. It's gonna take forever. I shouldn't have done that print. So if you guys haven't printed it out yet, don't print it out, okay? I think I'll have to do the magic trick over here, which is the alt control delete. Let me open k-means again. I am gonna definitely comment out I'm gonna remove the print statement there. Okay, don't print anything, that's fine. Okay, printing it out, Windows doesn't like that. Okay, so but we are getting like 4 numbers over there. Okay, so let's say you got 0, or let's say 10, 5, 8, 7. Okay, so this is the kind of result that you might get in this variable over here, which is distances of x to the centroids. Okay, now I want to assign myself to a cluster which has the minimum distance from me, right? So first let's create an numpy array over here, which is gonna store the list of where each point belongs, right? So I need to make sure that I know where I am. So I'm gonna say clusters over here, and I'm gonna say np.zeros, because initially let's start with saying that everyone is in the 0th cluster. Okay, and this should be for all x's. Okay, so if based on how big our data frame is, I'm gonna create a length of, I'm gonna see how big my, in this case we have like 30,000 points, so it's gonna create np zeros of 30,000. Okay, so now that I know that this variable is gonna keep a track of which cluster each point belongs to. So let's say I come over here and I get an array like this, or a list like this. So you were running this for loop. The first point comes over here and calculates the distance from all the centroids. Okay, so that point comes over here and asks, oh, how far am I from the first cluster? It says 10. How far am I from the second cluster? 5, 8, and 7. So based on this, which cluster should it mark itself to? The one which has minimum distance, right? And which the cluster 1 has the distance of 10, the cluster 2 has the distance of 5, distance of 8, distance of 7, right? So distance of 5 is the minimum, so it should go to the second cluster, right? So it should mark itself as the second cluster. So what we need to do is return the index of element which is minimum in the array. Will everyone agree to me with that? We need to return index of the element which is minimum, right? This is what we need to do. So now I'm gonna let you go and search on Google, and your hint is we are gonna use NumPy to do that. So use NumPy, and which method from NumPy library will you use, which will help us return the index of the element which is minimum in a list. Yep, Jai got that right as well. We are gonna use the argmin over there. So here's how you would go about writing that. So let's come over here. We need to find the index of the element which is minimum, right? So let's say np.argmin, and we're going to say distances of x to the centroids, right? This is the list which has the, now this will return second index, right? We need to get the index of that element. So we got second index. Now we are in the second cluster. So we know that this is in second cluster. Now where do we store this? We have already created an array over here, which is storing the list of all the clusters where each point belong to, right? So we are just gonna use clusters of I. So the ith element of cluster, which is in this case first point, will be assigned to second cluster because it was 10, 5, 8, and 7, right? That's what we saw, something like that. We are closest to the second centroid, so clusters of I will be 2 then in that case. All right, so let's go to the second part over here. Once we have our clusters assigned, what was the second step? The second step was find the new centroids, right? We need to find the means of all our points and then move our centroid to that location, right? That's what our step was. If in case you are not sure, let me go back over here. We did the first step over here, right? So we initialize k randomly. The first step we are done. We assigned colors, right? We said which cluster I belong to. The second step is to make sure that I see what all points are there in this cluster and then take the mean of all those points and then move my x to that point. Okay, so this is what we are going to do in the next step. So let's come back over here. Now I need to write a loop for I Now I need to go from only 0 to k, right? Because I'm just trying to move my clusters. So now this line is a little tricky over here. Okay. So what I'm going to do is actually write it first and then explain it. Okay. So let me just write it out. I'm just going to say points. I'm trying to find all the points. And I know that all the points, I want to store them in an array. I'm going to say for a point for j in range length of x, I want to go through all my points in x for j in range length of x if clusters of j, I mean if cluster of that point is equal to my index over here, right, for my k centroid over here, right? So this k is 4 over here, right? So I want to say for I in range of k, I want to say if cluster, so if I'm in 0 cluster, I want to add that in the point. So I'm going to say I over here, right? And for all these things, I want to return actually that point itself. So what I'm saying is for a point in this x, go through all this point. If I'm in that point, return the entire point itself. I'm trying to find all the points which are in my cluster over there, right? So I'm trying to get all the red points which are in that cluster. Go over all the points. If that cluster assigned in this previous step is equal to k, or in this case, because we are calling it as I over here, if I'm in that cluster, return this point itself. Let's go ahead and let's complete our program over here. So we're going to say we want to assign a new centroid, right? So I'm going to say C of I, this new centroid C of I location is equal to, I want to be at the same location as the mean of all my points that I just got, right? And I'm going to say axis as 0 over here because I want to calculate the mean around the first axis, the 0th axis. Okay, so looks good. The only thing left is we need to update our change in C as well, because we need to say change in C is equals to distance. We have already done this before, but we need to do it inside the loop. So we're going to say C old, and again none. Okay, there is one more thing that we are missing. So we are going to say show plot over here. So because we need to use this function show plot, which takes in the centroid C and all the x's, so which is going to show all our plots for all the iterations. So I'm going to say C and x. I'm going to pass C and x to the show plot over here. And let's just say plot dot show again so that it sticks over here. I hope it stays over here this time. So we are missing one last piece of puzzle over here. Okay. And I want you guys to think in this line, what are we missing? So when you are updating a variable, right, we have done this so many times before as well in our data structures programs, or no, many times, where we keep a track of the history of that variable. So what are we missing? We are keeping a track of this change in C, which is C and C old. But are we updating the C old? Right, Grusha got it right. We haven't updated the C old. So we need to say something like C old is equal to C, right? Now, but if you do that, what's going to happen is, no, it is just going to take the reference of C. If you are, a little bit proficient with Python, even if you know some basics, you know that when you do this, it is just going to assign a reference to it. It is not going to store it. Okay, so next time C old, when you update C over here, C old will get updated as well. Right, so that's not what we want to do. We need to create an actual copy of it. And that's the reason we have imported deep copy over here as well. From copy import deep copy. So we need to use this deep copy function or the deep copy method to, instead of saying c old equal to c, what we're going to say is, before we do all this, make sure that you copy it. So I'm going to say over here c old is equal to deep copy c. Before I update my c and I do anything else, I want to make sure that I copy the c, the previous c, right? Because over here I'm changing my c, so it should be over here somewhere. Let's see if this runs and if we haven't made any mistakes. Right, so seems like something is happening. So we have 4 clusters over here, and now the clusters move, right? So now we have the blue cluster, which is, it is trying to move over there, right? But it can't move anymore. It seems like it has converged to this solution right now. Okay, and hopefully after it doesn't move anymore, it will converge, and it, you saw that we just got out of that loop, right? So seems like c equals to 4 was not giving us that much of, what you would expect, because there were 3 clusters that we could see over there, right? And we are starting at random locations. So based on where you start, you're gonna end up with different answers. So let's try with k is equal to 3 and one more time. Let's try to run this. Right, so seems like with right now we have already started with a good looking answer there, right? And now you see that all our centroids have marked all these as blue, all this as red, so it is going to converge pretty quickly. Let's try to run it one more time with hoping that we get bad values of random points initially, right? So that we don't end up with a good answer. This is a good value as well. Let's try out sometimes. This looks like kind of bad answer, but still, all this is green, all this is blue. Now you're gonna see that the centroids are gonna move, right? So this centroid moved over here, this centroid is still over here, and eventually it is gonna color all these things over here as red, all this as blue, and all this as green, right? So that's what we had in class for you today. So thanks again for coming, and I hope to see you guys in our future sessions. Bye.